In this exercise, we have a transformation t from R3 to R3, a linear transformation, and it's given with this formula. And our task is to find a formula, if possible, to define the inverse of t. So we're assuming that t does have an inverse. And if it doesn't, we'll soon find out that it doesn't. Now, t inverse, or we write it t to the minus 1, what this means for it to be an inverse is that if t takes a vector x, y, z to rs t, the source and the destination are both R3, then t1 will do the reverse job. It will take rst and give us back x, y, z. That's what t inverse will do. Now we have the formula for t of x, y, z, which is this, and so what we do is equate this to rst. When we equate vectors, we equate them component-wise. Each of them is a vector in R3, so we get three equations, or if you like, a system of linear equations. X is equal to r, for x minus y is s, and so on. The rst here are like given, and we've got to find x, y, and z in terms of rs and t. Now, this system is not exactly in row echelon form, kind of just from top down instead of bottom up. We can still use method of, it's not going to be reverse substitution, it's going to be forward substitution. Look, x is already equal to r, we have that already. And then we can get y from here. Y is, what would that be, 4x minus s. But we have x from here, so it's 4r minus s. And then in the next one, we've got z as equaling x plus 4y minus t, but we already have x and y, so we plug those in, so then we get z in terms of rst. So we've got x, y, and z in terms of rst, which means that we can write this, that t inverse of rst is the x is here, the y 4r minus s is here, and the z from here is here. But now we can change the letters that we use. We don't need rs and t anymore. We can go back to x, y, z, and just dummy variables, but it's customary to use x, y, z where possible. And rst was an intermediate phase. Okay, so now we have t inverse,